My name is Dongju Lim, and today's topic is modeling personalized recruitment response to exercise and environment factors with wearables data. Let's start with reading our abstract. I assume that you read the abstract. What is the gap sentence?
However, these models are limited to small study.
Yes, I think so. This is a gap sentence, and how do you think about this abstract? I think this abstract is quite clear. They showed what they did and what they will show us. But yes, let's start. So I think there is a problem in the file. Maybe it is not correctly. So if we do the activity, then we need more oxygen. So to supply this oxygen in our body, we need more faster heart rate. So it means that if we do activity, our heart rate will goes up. And this process is not identical for all individuals. But for example, if I do this stairs for 10 minutes, then my heart rate will increase from like 60 to 150. But if the some marathon player do the same thing for this one, then maybe he or she, his or her heart rate will increase like less than me. So it means that this marathon player has better cardio respiratory fitness. So to experimentally measure this kind of cardio, what the standard method is, you let him or her to do exercise and measure the amount of the oxygen he or she took, and divide this amount of oxygen by the body mass and the exercise time. So we call it VO2 max, and this VO2 max is one of the measures we can use to quantify our cardio ability. So to measure this kind of cardio, we need some experiment, but by the advancement of the wearable technologies, we have the data of activity and the heart rate every day. We can easily obtain this activity data and the heart rate data. Then, from these two data, we may infer this cardio without any experiments. So one simple way to do this is using a mathematical model. Mathematical model relating this to activity and heart rate. So we can use to do this. We can use really simple mathematical model. So first, so it has three variables, and the first equation is this, and this means that oxygen demand increases when you are doing exercise. So if IT increases, DT increases. Really straightforward. And the heart rate, it looks difficult, but for this first few terms, this is just for restricting the heart rate between the minimum value and the maximum value, which is some parameter of this equation. And the last value is also straightforward. If we need more oxygen, then our heart rate should be increased. So it is just two equations with really simple mathematical two equations. Then but the problem here is that as you notice, there is f function here. But the problem is we don't know these f functions. It may be like some really linear, or it could be some function like saturation. But we don't know what is the f exactly. So one idea is that if we don't know this f function, then the problem is we cannot simulate, and that means that we cannot estimate the parameter from this equation. So what we can do is, because we don't know this function, idea is we can just change the function, or substituting this function with neural network. Then if we substitute this function, unknown function, with neural network, then what we can do is we can for each parameter of the neural network, we can simulate the heart rate rhythm. Then this heart rate rhythm, the simulation of heart rate rhythm will depend on this lambda, which is the neural network parameters, and the other parameters of the equation. Then what we will do is we will compare it with the data. And we will find the best these parameter combinations, which minimizing this loss. Then we can identify the neural network parameter lambda, so that we know this f function. That is a simple idea. So by using this formula, we can identify the function f, and we can identify the whole equation. I mean this whole equation from the data. But the one thing we should consider is that if we fit the data, if we fit this equation for one individual, then there's one parameter combination for one individual. I mean, one individual share same BA like alpha, beta, like lambda. However, it is not true because our cardio can be changed every day. So, for example, let's say that I started learning in January 1st, and I learned January 2nd again. And I did it every day, and I did it until December 31st. Then, compared to January 1st, my cardio at December 31st should be improved because I exercise a lot. So it means that depending on my previous activity history, my status is changed every day like this. For January 2nd, my state is like G2, which is depend on the exercise history in January 1st. And for the December 31st, my cardio state is G365, which is depending on my previous history for 1 year.
So Z means number of exercise? Or
It is like kind of combine or aggregate information from my previous history. So it is kind of conceptual. Like you can just think that it is my latent status related to the cardio. So it means that we have to incorporate this changing Z in these two equations. So if we change this equation, we have to change the equations like this. Every parameter in mathematical equations, like B, A, or alpha or beta, should be depend on the Z, which represents my cardio state. And this neural network function also should be depending on my cardio state Z. So this is the exact formula of this equation. And also we can, one another thing we can consider is the effect of weather and the effect of activity duration.
So here Z is given?
We have to estimate.
Using this equation or?
Yes.
Oh.
So is this normal for individual person or the whole population?
It is whole population, but it is whole population, and this G is determined by our previous data of activity and heart rate.
Oh, because I don't know how the Z is determined, because is there any restriction or rule for the Z? If G is any free variable, then we can make any simulation.
G. I will explain it
Explain
further. And so what we will do is, if we want to predict the heart rate during this workout, I mean for just 1 hour, then what we will do is we will find Z from our previous activity histories, like this. And from this Z, we will infer the parameters of the OD, what I showed you before. And using this OD, if we have the activity data here that work out, then we can predict the heart rate, like this figure. So what we have to do is we have to make a encoder model which predicts this latent status G from our historical data, and the decoder which produces the OD parameters from the our latent state G. So to do that,
이거 다시 한번 해야 될 것 같은데 쉽지 않은데 다시 처음부터 해볼까요?
so our goal is predicting the heart rate during the workout. So workout means that we are not working out every time. We are doing like 1 hour for every day. Then what I want to do is I want to predict the heart rate during the workout today, maybe just for 1 hour. Then to do that, what we need is we will use the mathematical model. I mean previously mathematical model I showed previously, and to do that we need that latent state J, and this G will be determined from our previous activity histories. Our previous activity.
The green one, the 1, 3, 4.
Yes, this green thing is Z, and from Z we will infer the parameter of the OD, that alpha Z, beta Z, and AZ and BZ. And using these parameters, we will simulate the OD so that we can predict the heart rate. So to do that, we need this encoder model for the estimation of Z, and the decoder model which calculates the parameter value from the Z. So to do that, they again use neural network. For example, for this encoder model, they use convolutional neural network. And the reason why they use this convolutional neural network is that, as you can see, this is the historical data, and the data lengths will be changed every time. So to accommodate this changing data lengths, they use convolutional neural network, because convolutional neural network seeks the feature by some changing window, so it can be easily accommodate the data with varying lengths.
Okay. So everyone, I think you should remember what Dongju just said. So if you go to typical machine learning and AI talk, people they just say that here is data and we use the convolutional neural network and here is the result. That's why people hate that AI talk. So whenever you said we decide to use certain algorithm, we should tell them why. Okay, this is very, very important to give a insightful talk. Thank you, Dongju. So everyone is okay why the CNN is useful for this case? Good.
For me, that Z variable is accumulation of history.
Yes.
So for me, it feels like something like sleep pressure.
Yeah, exactly. That's why we can use this kind of thing for your work as well. So kind of the point is, yeah, maybe the CNN could be a way. Kind of, at least we know that now the CNN is a good structure to analyzing the kind of updating historical data set. So, Jinu, kind of, our concern was also the data length issue. That's why you think that the CNN is a good way to do it.
한 가지만 더. 그러니까 원래 CNN은 그림
그치, 그림이지.
네.
히스토리가 누적이 돼도 이게 지금 쓸 수 있는 거죠. 아니면 어떻게 되나요? 그림이 잘려 나가요. 히스토리가.
그림이 더 커지는 거 아닌가?
네네, 약간 그림이 더 커지는데
네.
CNN 자체가 약간
계속 줄이고 할 수.
네, 약간 윈도우별로 이렇게 피처를 뽑고 그러면 예를 들어서 뭐 4x4가 있으면 뭐 2x2로
줄이고.
이렇게 하면은
네.
3 곱하기 3으로 줄여들고 막 그런 식으로 되잖아요.
아 그럼 우리가 원하는 크기까지 줄 때까지.
그렇지.
네네,
그런
약간
그런
그렇지.
그럼 yes.
The CNN, yeah. Don't maybe you can repeat in English.
yes.
So I think this is very good for us. Maybe you can use the blackboard. This is the key.
So like some spirit of convolutional neural network is that something like if you have this 4x4 input, then it kind of extracting the useful feature from this first 2x2 window and this next 2x2 window and repeated this for every like window, every like type, then it will be reduced to the 3x3. And if we do the same thing, it will reduce to 2x2. Then it means that even if with our data increase to like 5 by 5, then it can be eventually reduced to the level what we want. So this is why the CNN can accommodate the data with foreign banks. Yes. So like key point is that they use like there's two like key methodological points in this paper. First is they substituted the unknown equation with neural network, and second thing is they use this CNN to infer the like our cardio status. So for this whole structure, then by feeding this whole structure to the first 80% of each user, then we can infer the whole parameters of this convolutional neural network and other neural networks in the mathematical equation. So we can, by using that kind of parameters, like trained parameters, we can predict the remaining 20% of the workouts. So if we do that, they did it and they exactly accurately estimated the heart rate. So in this figure, there is black line and red line, and black line is the real true heart rate, and the red line is predicted heart rate. As you can see, this red line accurately follows the trend of the black line. And this is some representative example. And when we calculate the error from error, then compared to the really just normal time series like prediction tool, it decreased the error like this. And if we only check the error for first 2 minutes, which shows really steep increase and which is considered to be hard to predict, then it also the error for this prediction is also reduced by half. So, and beyond the prediction of heart rate, we infer this our latent cardio fitness Z. Then maybe this Z contains some useful biological information. So this Z is previously originally 32 dimension, but for the visual representation, the authors projected this Z for first 2 pieces, and they plotted this kind of heat map. In this heat map, this x and y axis is 2 pieces, and the color here is the value of the real VO2 max. Then if you see this, you can see that for this right corner, the color is darker, and for this upper left corner, the color is brighter. So it means that for this right corner, the VO2 max is low, and for this upper left part, the VO2 max is high. So it shows that this G is actually has some correlation with the VO2 max. So what they did is, using this G, they tried to estimate or predict the VO2 max. So this is the result, and if we only use the demographic information to estimate the VO2 max, you have this kind of error. But if we use both demographic and Z, then this error reduced to half. So it actually improves the prediction of the VO2 max. And even if we only use only this Z without any demographics, then it still shows reduced smaller error than using only the demographics. So this is all. To summarize, they used some mathematical model combined with the convolutional neural network and neural network, and they accurately predict the heart rate, and they infer the personalized latent states Z, and this was actually correlated with the real biological indexes such as VO2 max. Thank you.
Very cool. Yeah, any question?
So I think let's check. So is wearable data is whole continuous, or is there a gap? For example, they measure only when they are doing exercise.
I'm not sure, but what I'm sure is that they only use the data that they use has some gap. So 1 hour yesterday, 1 hour today, 1 hour tomorrow.
Yeah, then I think we have the issue of initial condition things for it every segment.
Yes, I see.
So maybe we need to check how they choose the initial condition for each day's that segment.
Yes.
And also, yeah, and for estimating Z, we need to also how they consider the time of day, or they just concatenated whole, just segmented data. So I wonder about this.
Time of the day. So So for this prediction, this is if it is this 1 hour, during this 1 hour, G is same, but G is changed like by the scale of day.
Day.
So for the each workout, our G is different, but during the same workout, G is same.
And maybe we could improve this if we can consider the time of the circadian rhythm days here. But not sure they have that information. But anyway, we have activity data, so then we can infer the circadian days there. And if we add that information, can we improve the prediction?
Yes, heart rate response could be different depending on time of the day.
Yeah, that's fine.
Because depending on when you exercise in the morning or night, the heart rate response could be different. I see. Maybe, yeah, indeed. If we add our estimated circadian days, it could be improved.
So the data size was over 100,000.
One data size, the N is like around 7,000.
7,000.
If we calculate the all workout, number of workout, it is around 200,000.
Oh, okay.
동민아 오늘 미나는 어디야?
학교 수업 갔어.
10시 이거 한가요?
아니 수업 이런 걸로 알고 있어.
아 그래? 우리 미나 때문에 이거 10시 오는 거 아닌가?
저 확실히 잘 모르겠어.
들어가야 될 것 같은데. I think this is a very, very important work. So I think we can use this kind of thing for nearly everyone's current project. So please think.